So, we will continue our discussion of mode locking and then go on to something called cavity damping. This is where we have got until the last module. We have discussed active mode locking using a mode locker by applying a sound frequency using device Sears effect within the Raman-Nath regime. And then we moved on to talk about passive mode locking, where what is used is saturable absorber. So, and we have finished our discussion saying saturable absorber can not only produce pulses, but they can also narrow them down. Okay. Now, what I want to say is saturable absorber works even better if it is not given the work of producing pulses as such, but pulses are produced already and the only job of the saturable absorber is to narrow the pulses down, and that is achieved very commonly in dye lasers especially, and also in some kinds of solid state lasers by what is called synchronous pumping. In synchronous pumping, one pumps the dye laser with not a CW laser, but with a pulsed laser. So, what happens if I pump with a pulsed laser? What kind of an output do I get from the dye? We are talking about rhodamine 6G dye lasers. I have a rhodamine 6G dye laser. I pump it with a green light 532 nanometer, but that 532 nanometer light itself is say 20 picosecond pulses, 80 megahertz or something. What should the output of the dye laser be? Okay, I will give options. Will the output be CW or will it be pulsed? That was a very simple question, but I am exciting with a pulsed laser. So, if I excite with pulses, should the output also not be pulsed? Why? The pulses are 20 picosecond, lifetime of the dye is say 10 nanosecond, say 5 nanosecond, and repetition rate is such that the difference between two pulses is something like 20 nanosecond. Should I not get pulses like this? Every pulse of pump is going to produce a burst of red light, and when the pump is off, then what will happen? There is nothing to produce a burst, isn't it? So, you get an inherently pumped laser, but the problem is these pulses that you produce are going to exactly, they are not going to be sustained unless the cavity length of the dye laser is exactly the same as the cavity length of the pump laser. Okay. So, you have to carefully match the cavity lengths of the pump laser and the dye laser. This is called synchronous pumping. Pumping is by a mode locked Nd:YAG laser or something like that, and cavity length is the same as that of the not pumped laser, I made a mistake there, pump laser, laser that is used for pumping. Okay. So, already the pulse is there, and then without going into the math once again, there is this 1978 paper which says that in synchronous pumping, pulse duration of the dye laser is square root of that of the pump laser. So, by synchronous pumping, you can actually get shorter pulses than the pump laser itself. That is why this was a very common technology for a couple of decades before the advent of titanium sapphire lasers. Okay. So, square root of that of pump laser. So, the good thing is it is not very difficult to produce a pump laser which has say 20, 30, 50 picosecond full width of max, but let us say you have 25 picosecond pulse width laser that is used for pumping. Automatically the output of the dye laser is going to be 5 picosecond, right, square root of that of pump laser, right, and I am asking you to believe me on this, we will not do the math. If you are interested, please read this APL paper from 1978. All right. Now, I should show you some result. This is the result. Kafka and Bayer, I think, were engineers working in spectrophysics, if I remember correctly. And this is what they produced: Nd:YAG, pulsed Nd:YAG pumped, synchronous pumped, rhodamine 6G laser. What is the full width of maximum that you read here? 220 femtosecond. So, if your pump laser itself has a short enough pulse width, then you can actually go down to 220 femtosecond just by synchronous pumping. That is how good it is, right. But then later on they modified the cavity a little bit. Kafka and Bayer may not be from spectrophysics, I might have made a mistake. This optics letters is from spectrophysics. So, this is again a laser. Do you see the cavity? Let us look at the cavity carefully. Here we can right away see some elements that we have discussed earlier, right. We see our familiar 4 prisms, and that is what will give you tunability anyway. Here this is the output coupler, the partially reflecting beam through which the light will go out. Of course, in the other end will be the high reflector, and this is what the pump is. Now, we have discussed I sapphire already. Do you see a major difference between pumping geometries of sapphire laser and dye laser? Remember, in titanium sapphire laser, the pump green light went through one of the mirrors. We said there is a dichroic mirror inside sapphire. Why? Because in case of solid state lasers, you get the best result if the pumping is coaxial with the laser lasing axis. Not so in case of dye laser. In dye laser, pumping can be at some angle. That angle is also optimized. Another thing I would like to draw your attention to is what is written here. What does it say? Gain jet. What does that mean? Gain, of course, means gain medium, rhodamine 6G dye. What is the meaning of jet? So, as you know, when very short pulses go through any medium, they get broadened due to chirping and all. So, in order to get short pulses which are picosecond or lesser, you do not want any extra component to come in the path. So, gain jet means in these lasers what they do is the dye would be stored in a small bucket, and it will be a lot of dye, say 1 liter or something, a lot of dye solution rather. Okay, and typically this solution would be in glycerol or some such very highly viscous solvent, and there used to be a pump which would circulate this dye. Okay. So, it would circulate and bring it out through a jet. Jet means a metal nozzle which would be flattened. So, the output of the dye through that nozzle would be a flat jet. Spherical, usually if you take a hose pipe, what kind of a jet do you get? The cross section will be circular, right? That will not work here. You want it to be flat and as thin as possible. That is why that jet was made. It was very, very thin, and then it would go into a catcher tube which would be connected to the reservoir. It would go back there. Okay. This was the state of the art again for about 20 years or so in picosecond and femtosecond lasers. One would use jets, and in fact, even now a lot of people do pump probe experiment where the sample is not a rotating sample or translating sample or anything, but a jet, because then there is no quartz coming in the path, no further broadening of the pulse. If you really want to go down to small time scales, jet is the way out. Okay. But I digress too much, right. And then here you have this gain jet, and here do you see there is a saturable absorber jet. What is that? DODCI once again circulated in the same manner. So, now you see this rhodamine 6G is already pulsed, and you know how good the pulse can be. What did you say? 220 femtosecond or something like that. Now, the question is, by introducing this saturable absorber, is there any improvement? And this is the answer. What is the full width half max now? 65 femtosecond. No, the lower number is correct. I do not know why they have written 100 there, but I checked with the text. 65 femtosecond is what they say. So, from 220 femtosecond it has gone down to 65 femtoseconds, because now think 220 femtosecond pulse, right. That means the base would be something like maybe 400 frame per second. From there to say 200 frame per second or so, for that time, that is the time required for the light to actually get absorbed, even of the intense pulse, and to have an increasing amount of bleaching. When the threshold is reached, then only the pulse propagates. That is why the pulse is narrower. Okay. So, synchronous pumping with saturable absorber for a long time used to be the state of the art for producing short pulses. Of course, now it is a thing of the past. Nobody would do anything other than titanium sapphire laser, but it is important that we know the principles, at least qualitatively. That is why we are discussing this. But everything said and done, nobody likes to use dye solution and all that anymore, because first of all they are messy. Secondly, dyes degrade very fast, especially saturable absorber. Rhodamin 6G is stout dye, not much happens. But DODCI is extremely flaky. I have worked with this kind of a setup. We would make a DODCI solution today and it would be very intense dark color. Within a matter of week, there would be no color in the jet at all. It will be bleached completely, because if you leave DODCI solution on the table under tube light, it will get bleached. So, that is a very big problem. And then when you are done with it, where do you throw so much of solvent? And there is 100 other paraphernalia there. Whenever you have solvent, your pump can go bad, the solvent chamber can leak, you have to cool it. It is really messy. So, that is really a thing of past now. So, right now what everybody wants to use is your solid state solutions, and something that is used now very often is a passive mode locker made of, well, not made of is perhaps not the correct term, something what is used is a saturable Bragg reflector which act as saturable absorber and therefore passive mode locker. But I should explain what a saturable Bragg reflector is. Even before going there, I should tell you what a Bragg reflector is. Does anybody know what is a Bragg reflector? Okay, whenever we say Bragg, what do you think? Diffraction, right? Whenever you say diffraction, what comes to your mind? These alternate layers, right? A lot of apertures and all that, right? So, a Bragg reflector is something like this. You have sort of a mirror, and in the example that we discuss here, the reflecting surface is gallium arsenide, and then you have alternate layers of high and low refractive index. So, when light falls on it, what will happen? Light goes in, first of all. Let us not worry about this thing on the top. From this direction, light goes in, gets reflected, comes back. But then when it comes back, since you have different layers, what kind of light will come out? Let me take the question down to an easy level. You have a grating, okay, or you have this crystals and all. Light falls on it, then light goes back. Everybody knows the rule which tells at which angle it will come out. What is the rule? Bragg's law. What is it? N lambda equal to 2d sin theta. I am asking an easy question. I never ask difficult questions. So, where does n lambda equal to 2d sin theta come from? Again, answer is easy. So, remember what you studied in childhood? You have one reflecting layer, another reflecting layer, right? So, you get a reflected ray from the first, another reflected ray from the second, and then what you do is you have to say that you have to have constructive interference. So, path difference must be integral multiple of lambda by 2 pi, lambda by 2. Okay? That is how you derived n lambda equal to 2d sin theta. So, in other words, so this is a Bragg reflector, is not it? What I just discussed, your crystal or whatever, it is a Bragg reflector. And what is the property of the light that comes out? All the rays that constitute that beam are in phase, yeah, right. So, now if you use a reflector like this, light that goes in and then light comes out, whatever light is able to come out of this Bragg reflector has to have components that are completely in phase, or in other words mode locked, right. So, when you use a Bragg reflector, automatically you get mode locking. So, this is the state of art. We have it a little later in the slide, where these are used as auto start Ticephalon lasers. You might remember that in one of the previous modules I told you that when we worked with homemade Ticephalon lasers, to get the mode locking started, we had to tap a mirror. In the tsunami that we have in our lab, there also to get the mode locking started, we have to disturb the cavity a little bit. However, in MITI, the new laser that we have, the compact laser, we do not have to do anything. Why? Because MITI uses a saturable Bragg reflector. And we have not even got to the saturable part, Bragg reflector. Okay? So, automatically light that comes out is mode locked. Okay? So, that is why one wants to use Bragg reflector. And if you want it to be a saturable Bragg reflector, what you do is you introduce what is called a quantum well. Okay? The substance is written here in the what it is used. What is the meaning of quantum well? You have substance with small band gap sandwiched between two layers of another substance which has large band gap. So, once the exciton gets trapped there, it is not so easy to come out, right. What does that mean? When will it come out? When intense light falls on it. So, that is the saturable absorbing action. Okay. So, Bragg reflector with a layer of quantum well is the saturable absorber of choice in present day. Nobody uses DODCI anymore. DODCI sales must have fallen worldwide. You might, of course, this is made by layer assembly. And this is an example, and what I want to draw your attention to today is how old the technology is. 1995, 1978 I told you is when femtosecond pulses were already there. 1995 is when you have the use of saturable Bragg reflectors. The diagram you see here is for a diode pumped solid state laser, and I think you can more or less make out all the components, what is going on. This here is a saturable Bragg reflector, SBL, okay, and that is what causes passive mode locking. What is the full width half maximum here? 100 femtosecond, not as good as 65 femtosecond, but it is so hassle free that nobody cares. And also the comparison may not be fair, because there you had a synchronously pumped dye laser with saturable absorber. Here you have a diode pumped solid state laser. Inherently pulse width is going to be more. But then now I show you another one from the reference is there in the same paper, and it is there in a laser focus world article as well. This is a self starting Ticephalon laser. Once again you see the there are two different cavity designs, but the crux of the matter is that this saturable Bragg reflector is used as one of the mirrors. Now see what the pulse width is, 25 femtosecond. So, good thing is, first of all, Ticephalon itself gets mode locked by KLM. Into it you are introducing a saturable absorber. So, the output is as good as it gets. So, in all not all, but in most of the modern day compact self starting Ticephalon lasers, this technology is used. Now, we move on to something that is a little different, but it is very easy to get confused between the two. So far we have been talking about mode locking, right, how to produce a short pulse, maybe not an ultra short pulse, but short pulse nevertheless. And why not an ultra short pulse? We have showed you that you can go down to 25 femtosecond by mode locking. Next question is, how do you get the pulse out? You can get the pulse out by using an output coupler. But especially in the dye laser era, the question that people asked is it possible to do better? Is it possible to use some other mechanism by which there will be further amplification, perhaps further narrowing of pulse, and we can change the repetition rate? So, I will give you an example. All those dye lasers, rhodamin 6G dye lasers that I showed you, they are synchronously pumped by green lasers which have a repetition rate of about 70-80, something like that. As you understand, if you want to do say fluorescence experiments, TCSVC experiments, 70 megahertz is too fast. You have to cut down the repetition rate. How do you cut down repetition rate? So, as long as dye lasers ruled the market, cavity damping was the technology. Unfortunately, titanium sapphire laser cannot be cavity damped. It would have been great if it could be. So, that is why you have to use something else called pulse peaking. But let us talk about cavity damping first. If there is time, we will talk very briefly about pulse peaking and then we will pick it up next day. So, in cavity damping, you use the same thing, you use an acoustoptic modulator, right. You take a quartz crystal or something and use a transducer. But now, you do not work in Raman-Nath regime anymore. This is the main difference. You work in what is called the Bragg regime, and Bragg regime condition is exactly opposite of Raman-Nath regime. Here L is much greater than capital lambda square divided by 2 pi lambda. Okay. That is where cavity damping is observed best. So, first of all, what do you have to do compared to a mode locker? You have to use a higher frequency of acoustic wave, right, because if L has to be much larger than capital lambda square by 2 pi lambda, you have no control over lambda, right. Lambda depends on what kind of laser you are working with. You do have control over capital lambda, which is the wavelength of light. So, if L has to be much larger than its square divided by some constant, then that capital lambda should be small, or in other words, the frequency of the acoustic wave should be large. Also, the other thing you have in your hand is the length. So, you can use a longer interaction length, all right. You can use thicker crystals now. Of course, there is a limit to that, because if you use something that is too thick, then again pulses will get broadened. So, you always have to find the optimal length, right. So, what happens when you work in Bragg regime is this. Remember what happened in Raman-Nath regime? Light passing through was diffracted on the two sides and was phase modulated by amount of n omega. Here that does not happen. All the higher order diffraction is eliminated, you do not get it. Why you do not get it? We have to read the original papers, but for our purpose we do not even need to know. You do not get higher order diffraction at all, only two rays are sustained, the 0 order, that is unmodulated omega, and the first order omega 0 plus capital omega. Okay. So, this is what happens in a Bragg regime. Okay. Have you understood what happens? Yeah, can I go ahead? Only two beams now, and that is important for cavity damping. And this is what a cavity damper is made up of. There is some math after this, maybe I will skip all of that and I will just show you the final result. You can go through the math if you want. So, here what happens is, first of all, now here we have an interesting situation. All this time we have been saying that in a laser you have a high reflector and we have an output coupler, right. In these lasers there is no output coupler, all mirrors are high reflector. So, in absence of cavity damper, what kind of a laser is it? You pump it, lasing will start, right, there will be gain, but there will be no loss, it will never come out, right. So, there is no output. Cavity damper is a device that is put into a laser like that to get the pulse out, to switch the pulse out. How? Okay. This is the same thing, it is a part of the laser cavity. On this side you can understand there will be the gain medium and all, and the other end, other high reflector. Here you can think this is the last mirror, M1 in this case is last mirror or first mirror, whatever it is. Since it is one, you can say it is a first mirror, last mirror is somewhere else, but the crux of the matter is no output coupler. Here you have M2, both are concave mirrors, focusing mirrors, and we have this AOM at the focus of both. Center of the acoustic modulator is at the focus of these two mirrors. Okay. Maybe I will just take this and stop and start from here next day. So, think of this horizontal line, the horizontal black line is the lasing axis, comes here, goes through. Now, this acoustic modulator is being operated in Bragg regime. So, what will happen? 0th order one will go through and there will be the first order line, which is frequency modulated by just a little bit. Okay. So, now you will have two rays. Then since, and it is constructed in such a way that these rays hit, well, I do not even have to say that, this one is at the center, right. So, these rays are made to retrace their path. So, now what happens? When they retrace their path, on this side also you will have two rays, understood? One of these will go back to the laser cavity. The other one, which takes a different path, will not go through the laser cavity, it is going somewhere else. You put in a prism there and it goes out. Okay. So, that is how damping is done. What is the advantage? We will start discussion from here next day, but what is the advantage of this? So, you see we have used a pulse speaker, right. What is the difference between cavity damper and pulse speaker? In pulse speaker, the acoustic modulator is outside the cavity. So, what are we doing? We operate the laser at 80 megahertz and we operate the acoustic modulator at 8 megahertz, right. So, we are taking 10% of the pulses, dumping the remaining 90% of the pulses. We will discuss later again. What is happening in cavity damping? Either the light goes out and you use it, or it goes back to the cavity. Nothing is wasted. And bunch of photons that go back to the cavity is going to get amplified in the next round trip, right. So, in cavity damping, this is the attractive feature of cavity damping. You take out the light, at the same time you have further amplification. So, whereas your power is going to get cut down if you do pulse peaking, you measure the power before pulse peaker and after pulse peaker. If you operate at say 1/10 ratio, your power is also 1/10, isn't it? Because you are taking only 1/10 of the pulses. But in a dye laser, first of all, if there is no cavity damping, you cannot even measure anything, no light will come out. But due to cavity damping, what you see is there is an increase in power, because while the light is taken out, only one part is taken out, the remaining part is sent back to the cavity. No photon is wasted, nothing is dumped. Okay. This is where we will start from next day.